Okay, now we're going to go ahead and add in step 4 for our 4 steps to linear analysis. Before I show you how to do this, I'm going to do a quick run through on everything we've done so far in the previous presentation. If we recall the initial problem, two students want to determine the acceleration of a car. They start at 0 miles an hour and they speed up, and every second they record the velocity. So we've already determined that the independent variable is time, the dependent variable is velocity, and all other variables are controls. We have the equation y equals mx plus b, and the equation velocity is v initial plus at. We recognize what the independent variable was in the physics equation. We recognize what the dependent variable was in the physics equation. And then we decided that knowing where those two variables are, we can rewrite the bottom equation in the format of y equals mx plus b. And we get this. This leads us to conclude that the y-intercept, also known as b, is the initial velocity. And now for the slope. The slope in y equals mx plus b I've highlighted in a yellowish gold color. You can see that it's multiplied by the independent variable x. So in the bottom equation, our slope, a, highlighted here in gold, is multiplied by our independent variable t. So a, the acceleration, is known as the slope. So if we follow our steps of plotting the data points, drawing the best fit line, we would be able to conclude by looking at the y-intercept. The y-intercept is the initial velocity. Then if we calculate the slope of the graph, acceleration is the slope. In any given equation that you're trying to model it in a linear format, the slope is the variable or variables that are multiplied with the independent variable. There can be more than one. In fact, in our next example, we'll see that there's going to be two. Let's try another problem. Students wish to determine the density of an unknown fluid using pressure. They will fill a beaker to various depths, and they'll use a pressure gauge to determine the pressure at the bottom of the beaker. Our job is to determine the density of the fluid from the slope of a pressure versus depth graph and the equation absolute pressure is atmospheric pressure plus the gauge pressure, which is also known as rho gh. Now this is the way here that we're going to see the problems worded on the AP exam. And what we're going to do is we're going to follow our 4-step process that we've been going through before. Step 1, we need to determine the independent and dependent variables in this experiment. Since the students are controlling the depth and making it as they wish, that's what makes it the independent variable. The pressure is what's changing as the students change the depth. That means the pressure depends on the depth, and therefore pressures are dependent variable. So y equals mx plus b is what we're aiming for. Let's highlight our independent and dependent variables. Here's the independent variable here, depth, and the dependent variable here, pressure. Now we need to rewrite the equation. On the left side, we should only have the dependent variable, and we do. Then it should be equals any kind of constants times the independent variable, which in our case is h, plus whatever remains, which is going to be this atmospheric pressure. So we're going to flip these two terms. Math tells us there's no problem with that. And there we go. It's clear to see that the y-intercept is this plus whatever remains, which in this case is the atmospheric pressure. This makes sense because no matter how you run this experiment on the surface of the Earth, you are going to have the Earth's atmospheric pressure pushing down on the fluid inside the beaker. The slope here in gold is whatever is multiplied with the independent variable. In this case, we have two terms, and there's absolutely nothing wrong with that. So the density of the fluid times the acceleration due to gravity, so rho g, is the slope, also known as m. There's no problems with this being more than one variable. What it does is, once we run through a format of plot the data, make the best fit line, figure out the y-intercept, okay, we've done all that. We calculate the slope, whatever number we get. Let's say it turns out to be 13,000. What that tells us is 13,000 is the density of the fluid times 9.81, or g. Then we'd say, okay, 13,000 equals 9.81 times g.